Hello everyone, this is the 8-bit computer which we made under our subject digital electronics in this semester, and in this video I will like to explain this project, and the related document of this project can be found in the description. There will be a link for the document. So in this 8-bit computer we have a total of we have divided this computer in 7 modules exactly. So I will be explaining each of them one by one. So the first module is the clock module. This is the clock module, and the second is the registers, and this one is the registers, and the third one is the ALU. ALU is the part of the register itself. This second one is the ALU thing. This uh, will show the addition of A plus B register. Whatever data in A and B will be shown here. And yeah, the third thing, we in this computer we will have RAM, which is this. Fourth thing, this is the RAM we will have, and the size of RAM in this computer is 16 bytes, which is as compared to a modern computers. Like my laptop has 24 gigabytes of RAM, which is quite a large. Like if we convert that into bytes, it will be approximately 24 into 1024 kilobytes, megabytes into 1024 kilobytes into 1024 bytes. So that is quite a float. Also the same for the clock. This our computer, this 8-bit computer will have a total speed of 1500 megahertz, only hertz, while the our modern computers have the speed of 1 to 5 gigahertz, which is too much compared to this one. While okay, so these are our 4 modules. The next one will be a program counter. This is the program counter. It will keep check of the instruction which will be get executed, or which one is the executing. So it will take care of two things mainly. The like it will track the instruction for a while. We will stick to that only. The next one is the output register. This one is the output register. This will display the data of the E register. Also, we are saying this computer as a 8-bit computer because the bus of this computer is 8-bit wide. 1 2 3 4 5 6 7 8. So the bus width of this computer is 8-bit, while our modern computers has a bus width of 32-bit and 64-bit. Like the one right now I am using has a 64-bit processor, means it has a 64-bit wide bus. And the bus is shared equally to both of these left and right side of this computer. Also, the next module of this our computer is control logic. This is the control logic. These are the symbols for the control logic, which I will explain later in this video. Mainly the control logic will automate all the things, like how the instruction perform the operation, like which instruction is going on and what will be control word according to that here, and the same will be get executed in this whole computer. Okay, so all right, I have explained all the I have just briefly explained the seven modules of this 8-bit computer. Now I will explain just more, like the things which I skipped. In our register there are 2 more registers are there. Like not 2 more, there is a this is another register which will store only data of 2. The first one will be the zero flag, the next one will be the carry flag. Zero flag will get on when there is nothing in the ALU, and the carry bit will get on when there is a carry or data overflow in our ALU. Like these are total 8 bits. If the data went to the 9th bit, which can be taken by the C out of the last adder which is used here. I will not go into the deep of that. You can check out the same in the document which is attached in the description below. So yeah, from the cout of the adder we can take a look at the carry and we can record that here. And this is our RAM. In RAM, our RAM has 16 bytes of memory sense, so these 4 LEDs denotes that which byte is there, and these 8 LEDs will denote the data in that address. It's like say this is the 0 address. Right now there is no light is blinking, so we'll say we will consider it is a 0 address, and the data regarding this is, and this right now it is all zeros. I will say the data in the 0 address of RAM is 0, and we in total have 16 address 0 to 15, and so our size of RAM is 16 bytes. And similarly we can say that these are the memory content of this corresponding to this address also. And this is the instruction register which we can see here. These 4 blue LEDs will denote the instruction. These 4 yellow LEDs will denote the address of the data which the instruction is pointing out. So these 4 are the instruction LEDs, these 4 are the memory address that instruction is pointing towards. So this is the instruction register. We will go deep later in this video. These are the cycles, like in each instruction in total we can have 5 cycles here, that is denoted by this section T0, T1, T2, T3, T4, and the maximum we can have 5 steps in one instruction. So this is the brief introduction of this computer. Also I just left one thing, this is the RAM part. These are the register that will store data temporarily. These are made up of D latches, and for these we have used the IC 74LS173, which about this you can find more in that document which we have attached. Also the ROM part of this computer is taken care by the EEPROMs. We have used in total of 3 EEPROMs, 1, 2, 3. This EEPROM is programmed for this display. Like this EEPROM will decode whatever the data in this bus and will be shown here. See, similarly these two EEPROMs are programmed like such a way that these will throw some data according to the instruction we have. So that data will be shown here exactly, and according to that the instruction will be get executed. Also to program these EEPROMs we have one manual programmer. We can program these EEPROMs by manually putting address, like latching address on one side and latching data on the other side, and we can program bit by bit. And the other we have an Arduino based programmer which we have used because we have to almost use 2000 bytes on each of the EEPROM. So we have used this Arduino based programmer. We have to put the EEPROM here and upload the code through this Arduino, and the Arduino will write the bytes. So these are the EEPROM programmers we used. Now I will like to on this computer and explain you guys some operations we can perform using this computer. Like since this has a 16 byte of RAM, we can perform anything which we can write under the 16 bytes. And the most basic programs like add, subtraction, multiplication, division, we can easily do on this computer. Also the most interesting program we have did was Fibonacci series. We can program this like this computer such like this will so the Fibonacci series 0, 1, like similarly it will goes on. And since we can program and we can achieve anything we want but the thing is the code is supposed to be under 16 bytes. If you have ever noticed, like when you program in C, like there is a section that how much memory that program has consumed. So we can write the program which is under 16 bytes. If we can write a program which is under 16 bytes, then this computer can perform. If the program can't be written in under 16 bytes, like the large one hopefully, so we, not why hopefully, but yeah, we can't perform those operations, those programs here. Just for basic, to keep this video simple, I will just perform an addition and a counting operation in this computer and explain the steps of those. First of all, I would like to power on this computer. So now the computer is on. Since I would like to do the addition operation, I would like to show you how our computer actually do the addition. So first, before that doing anything on this, I would like to take you on my laptop screen so I can demonstrate you how our computer performs the operation. So we are right now on our PC. So here we just hope a second, just a second. This is the code written in the C. Here we have a variable a which is 7, the other is b which is 3, the C is the addition of all these. Hopefully you can see it. Yeah, so this is the code in C where we have one variable a which is set to 7, another is b which is 3, and the result is a plus b, and the result is shown by this line printf. And now I will execute the same. Hopefully you can see it. See, if I perform the operation, just a second. So here we get 10 exactly, 7 plus 3, 10. Now the assembly language, or how the compiler understood this thing and how it translated to our hardware, which I will show you. So these are the assembly language, or these are the opcodes that program got broken into. Whenever I used this command to run, this was the command I used to run the program. This tells that we are using the GCC compiler, and the rest is, I won't go into that. Yeah, this is telling that we are using a GCC compiler to compile that thing, and the compiler does the thing is it translates the same into the machine code, which look like this. Like here on address, this address is shown in hexadecimal notation. So this is the address, and corresponding to this address, this is the opcode, or this is the assembly instruction which will get performed. Similarly, there are like this program in total consumed almost of 18 byte, I guess. So this in this C compiler broke that code into 18 something lines of assembly language, which was internally coded into the RAM, and that got executed, and we got the result as 10. Actually, we can see like we are getting the result as 10. So these are the instruction for adding two numbers in C by GCC compiler, which my hardware is made like this that it can understand the C language and compile it. So the same is fed to the my hardware, which is, let's say, our CPU, and the CPU did all the operations, and we have got the 10 here. So to achieve the same in our computer, we will not have to go through all these steps, because since this is our computer, we have designed the assembly for this of our own. So we can achieve the same in the 4 instruction itself. Before that, I would like to explain you guys all the instruction of a computer has, not all the, but the one we will use in this the program of addition. Just a second. So these, hopefully you can see, these are the instruction our computer or the programs I have programmed. With NOP will do nothing. LDA will load some value in the register A, and the add will load a value in the register B, and it will whatever that in the output will it will load again to that A, which is quite confusing, but yeah, that it is. And the next is subtract. Subtract command will do the load address loads data in the B register B, and we can perform A minus B. And STA command will lets the data of A register into the memory like this, and the last like this out will do whatever in the we have in the A register. It will put that on the bus, and we can see on the output register, which was that 7 segment display, and HLT halt, which will show our computer. So these are the instructions, but for the add command we will be using only load, add, out, and hold to stop the computer. Yeah, this is we will using LDA, add, and out, and hold. I will show you just a second. Before I show you the commands, I want to give an analogy. Say here it is written as a push, which is some opcode which will translate into some binary data, which will be understood by our hardware. Similarly, this is the data for our this 8-bit computer. These are the instruction we made. Say like this is the add instruction. These 4 bits which I have discussed in the instruction register, which was denoted by the blue LEDs. These 4 will tell the instruction. This is the opcode for this add instruction, and these are the steps on which step we are right now. We will not go into depth of this, but yeah, add command will have this data which will be executed. Similarly, corresponding to each opcode here, there will be some binary data which will be executed by the hardware of this laptop and hardware of this laptop. That is CPU. So similarly, our 8-bit computer or our CPU will do the same, but we will have different instruction because we are not having a C compiler. We have our own compiler, which is we have made our own assembly. So we will program the same in our own assembly language. Just a second. So this is our computer. To add 2 numbers, the program we have to write will be this: load, add, out, hold. And in the C language we have to write that A is this, B is this, and then C is equal to A plus B, and then printf, which will in turn print the value of C. So we can't do the same here because we can't. So this is these will be the commands I will be programming into the RAM of our computer. So for that I will switch into the programming mode. This is the programming mode for our RAM. So this is the address. So at 0 address I will, this is the 0 address. At 0 address I will load this command LDA 14. LDA in my EEPROM is stored as 001 as its code. So the first 4 bits will be instruction, which is 001 here, 001 here, and the next 4 bits is this instruction is pointing towards. So we are saying LDA 14 means it will pointing towards the memory address 14. So I will make this 14. So the 14 will be 110 in binary, and I will code the same in RAM. So this is the 0th address in our RAM, and the data in this 0th address is right now is LDA 14, which is load 14. And load 14 will do is that it will load the data of the 14th memory location into the register A. So I can show you the same. Say this is the it will load the data of the 14 address. So I will put some data in this 14 address. So this is the 14 address, 12 plus 4 sorry 8 plus 4 12 plus 2 14. So this is the 14th address, and the say I put the data in the 14th address is 3. 1 plus 2 is 3. So this is the data in the 14th address, and the 0th address having command load 14. So I will go into the manual mode, reset everything, and we can see the 3 coming into the A register. Yeah, so we can see that 3 had come into the A register. So our load 14 command will do is that it will load the data of the 14th instruction into the A register. So this is the load command will do. The next is add 15 command. Add 15 command will do is to put the data of the 15th memory address into the B register, and whatever is the output, whatever is the sum of A plus B, put that into the A register. There is no need to put into the A register, but we will be not putting the output in the sum register itself. We will putting it into the another register, but right now we have only 2 registers, so I will put it into the A register. Also the we have made the out command such that the A, whatever in the A register will be shown here, so we will be doing that. So the next I will go again into the programming mode, and this is our 0th address. So the data is got miswritten at 0th place. This is the load 14, and the 1 at the 1th place it will be add 15. This is the add 15 command. On the 3rd, which is out 0 1 2 0 at 0 address we have load 14. At the 1 address we have add 15. Now at the 2 address we will be having out, which will do is basically do is that whatever is in the A register, it will show it into the output register, which is this 7 segment display. So I will program that into the second position. We will have out. So this is the out instruction, and the last command is we would like to hold this computer because the addition is completed and we don't want to continue, so this will be the hold instruction. Yep. So now we have to add 14th and 15th, whatever data in the 14th address and whatever data on the 15th address. So I would like to put some data on the 15th and the 14th address. Say this is the 15th address and I put 7 here. This is the 7, 4 plus 2 plus 1, 7. And on the 14th address there is already 3. I will keep it as it is. Okay, so we have 7 plus 3 and the 3 is in the 14th and position, and on 15th position we have 7. So I will go again into the manual mode, reset everything, and now last time I was giving manual pulse to the computer, but this time I will be giving an automatic pulse which will perform operation by itself, and we can see the result here. Sorry for the last time, like it was showing 1, there was some error because this thing is built on the breadboard, so there are many factors which are not in our hand. Like there, if I hover my hand over this, like, so each wire have some magnetic field and electric field, and my hand movement can affect some, like it can generate some randomness, so sometimes it's behave not the way we want, so that's quite normal. So but yeah, the thing is we did 7 plus 3 and here we can see that 10 is the output. If we want to do the thing but this time fast, so I can increase the clock speed. This is the clock speed right now, and hopefully this can be visible in the camera. Now I will increase the speed of this. You can see that the LED started blinking more often. So the maximum speed the LED can blink right now is 1500 times in a second, which we can't see through our naked eyes. So yeah, we can't see it right now, but it is blinking 1500 times in a second, which is the maximum speed of the operation it can perform. So if I press the reset, it will see how fast it does the operation. If it do all the things, and we reach 10 again here, but this time it does at a very fast pace. So that was the addition. But say if we want to keep it slow, so we have to reduce the speed of the clock, and this time the operation will be in the slow speed, and that can be seen here. So now I will explain the same, but by manual clock, means by pulse I will explain it. For that I have to put it into the manual mode. Now it is in the manual mode, so when I press this button, then there is a clock, else there is no clock. If I put it in the stable mode, then whatever clock it here, it ends up here. But now I will put it in the manual mode, so whenever I click this button, then there is a pulse, else there is no pulse. So I will, this is the reset button. I am mentioning it quite often. So this reset whatever store in our latches. So this it, now we are here we have LDA 14 command, okay, at 0 memory address. LDA 14 command is consists of, like I also mentioned previously, we have in total of 5 steps for each command to execute. So for this load command we have 5 steps. The first step is memory in, counter out. In the first clock pulse, whatever is in the counter will come into bus, and also whatever in the bus will go into the memory. Okay, so right now in counter there is 0, so there is a 0 in the bus, so 0 will come here. So we will see nothing in this pulse. Also the same can be seen here. See, this is the memory in instruction which is on. This is the counter out instruction which is on. We can track here by here also and also by here. So at first pulse 0 is coming here and 0 will come into the memory address. So in this pulse nothing will happen. 0 was there, 0 came here. Now in the next clock pulse there will be RAM out, instruction in and counter enable. Now one thing I would like to clarify that whenever there is a latch involved, the latch will latch the data on the clock pulse, while if there is a out command, say this is RAM out, counter out, that will happen corresponding to that command itself. Like say this is the RAM out, so for RAM out we don't need any kind of pulse. The RAM out will happen the same time when it is on. See, the RAM out is on, the whatever data in the RAM is on the bus, but the instruction is also on, but there is nothing in the instruction. The data will come into the instruction but on the clock. So there will be no data like here, but on the next clock we will be having some data here. So the main point I would like to say it again, that if there is data to put on the bus, then it will happen simultaneously. But for that we don't require any clock, but for to latch something into the flip-flops we have to give it a pulse. So the next instruction at T1, at T0 we have memory in and counter out. T0 happened. Now we are at T1. T1 we will be having RAM out, which is already done. So for that we don't need any clock pulse. Instruction in, counter enable. So counter enable means the counter will be counting by 1, and instruction in will means that whatever in the bus will be in the instruction. So whatever was that in the bus was has come to the instruction. Also our counter has been incremented by 1. Now this is the instruction. Now it is 0001 which we programmed in our RAM, and 0001 corresponds to LDA, which is load command, which can be seen here. This is load command. Let me check this counter is visible in the video. Hopefully it is. Okay, things are not visible quite good in this camera, but I will try to explain as much as possible. Right now here is only one LED is glowing, the rest 3 are off. Also here we can't see, but we are on the second step which is not glowing. Yeah, so then there is an issue, but I will try to do my best to explain this. Yeah, so we are on the third step, which is instruction out and memory in. So since the instruction out will happen simultaneously, so this is in the instruction, and it is on the bus on the same pulse, and then on the next clock pulse there will be memory in. So whatever in the bus will come into the memory. So yeah, so on the next clock pulse there will be a memory in, whatever here it is, it will come into the memory. So there was 14, so 14 came into the memory, and the data corresponding to 14 is 3. So we can see it here. Again I will like to do it again quickly for you guys. So at step 1, whatever in the bus will come into the memory address, which can be tracked here. Memory in and counter out, counter outing the value 0, and 0 will come into the memory. And the next step is RAM out. RAM out is already done. The instruction, whatever data in the bus will come into the instruction. And next is the counter enable. The counter will be incremented by 1. Counter is incremented by 1, and whatever data was in the bus was it is in the instruction register. Now instruction is add. So our control logic, this control word or this microcode EPROMs are programmed such that when this instruction is fading in these EPROMs, there will be these commands will be running. So the next we are now on T2. How it knows I0 MI instruction out and memory in signal to be on. So this is instruction out symbol is on. This is memory in symbol is on. How it knows? This is because we have this add instruction which we have programmed in these EEPROMs. So according to this address, these is the data set it is throwing. So this is 101001000 like this. So we have on the next step we will be having memory in which is 14. So we have programmed the load 14 command. So this load 14 command is loading the 14th value in the address, loading the 14th address, and the corresponding value will be loading the A register, which we will see. But right now we are on the T2 step, which is say instruction out, which is already done. But here you will notice that instruction is not outing putting all the 8 bits into the bus. It will putting only the least 4 significant bits. It will never put the most 4 significant bits into the bus because these are the instruction. So we will not be putting that instruction into the bus. We will only put the first 4 bits, which are the memory address, which I told you earlier. So on the next clock pulse, whatever the thing is that will happen is that whatever in the bus will come into the memory. It comes into the memory, and we have 3 here. Now the thing is will happen is the RAM out. Whatever in the RAM will go into the bus, which is already there, and it will come into the A register. A in means register A in. So the 3 has come to the A. Now similarly we are on the T4 now, and the last step we have nothing to do in the last step. So there is no signal is on in the control board, so nothing will happen in this. Now again we are on the command 2, which is add 15. Now you can see the last time we incremented the program counter because our first step of each cycle says memory in counter out. So whatever in the counter it's come into the memory. So this is because we can execute in the cycle 0, 1, 2, 3, 4. So last time we did 0. Now this time it will load in the RAM the command number that is on the address 1. So the address 1 will be get load in the memory address. Now according to that on that 1 we have programmed the command add 15, which we can see here. So now here these 4 bits indicates which instruction. 0010 indicates add, which we can see here also. 0010 add indicates it's an add instruction. Now these 4 are the memory address this add instruction is pointing, since we have add 15. So this add 15 command is pointing towards memory address 15. So next on the next 2 clock pulse we will having 15th here. On the next clock pulse we will be having 15th memory address, and the data in the 15th memory address is 7. So on the next clock pulse the 7 will be in the B register, which we can see here. RAM out D in. We are on the 4th step, which is T3, because we are counting from T0, T1, T2, T3. So we are on the T3, and on the T3 there is RAM out D in. So on the clock pulse the data will be on the B. Also right now 3 plus 0, A plus B here, which is 3. In the next step A will be 3 itself, the B will get 7, so 3 plus 7 will be 10. So this is 3, this is 7, 3 plus 7 is 10, which is shown here in the binary. Now the next commands on the next cycle of the add command says whatever in the sum register, which is this, should come to this A register. Okay, so this is A in, sum out. Sum is already out in the bus, and the sum will be written in the A register on the next clock pulse. The sum is written here. So now I would like to do the same again, but this time quickly. So we will be having load 14 command. For at first load 14 will load the value of memory address 14 at the register A, which is 3. Now we will be having the data of 15th address in the B, which is this. On the next clock pulse we will be having data of the sum into the A, into the A. Okay, so we will having this data into the A. Now our next instruction is 0010, which is the out instruction. 0010 out. So out command is that whatever it in the register A, it will put in it into the bus, and it will show the same thing on this 7 segmented display. So you will see that this 7s come into this bus, and that has come here. Sorry, this 10 has I will do it again. So on the next clock pulse we can see we are having 10 here. Now output in signal is on, so that 10 will be reaching to our display. So we can see 10 here. The next command we have programmed into our RAM was hold. So this is the 0011. We first executed the load 14 command, then we executed the add command, then we executed the out command. Now we are on the hold command. So this time we will be doing the hold command. What the hold command is that it stops the way of these clocks into the master clock. So on these next three instruction, we can see this hold signal will be on, and the effect of this monostable pulse will not be seen in the master clock. Now the hold signal is on, and when I press this pulse, I am pressing it, but it can't be seen in the clock because we have halted the computer. So this was the addition of the two numbers in this computer, and it can be done automatically by if we on this. So it will show 10 and it will stop by itself. Similarly, we can program it in a number of ways, but for just a quick demonstration I will just do one more program which will count from 1 to 255, and we can have it in the many ways, but for now I will be doing it with the 1. This is the 1. This program will be using the jump instruction, which in turns stop the counter at the place where we want. So it at 0 address I have programmed this add 15 command. On the 1 address I have programmed this with the out command, and on the second I have programmed it with the jump 0. Jump 0 does it like on the normal day it should be doing 0. It should be executing the command at 0 address. Then it should be executing the command at the 1 address. Then it should be executing the command at the second address. Then after the second it is supposed to execute the command at the third address, which we have not given. So on the third address there should be a random data, there is a random data. So it was not a random data. Last time we have programmed that third position as a hold, so here is a hold data, but we don't want to go on the 3. We want to go on again on the this 0 instruction, because I want to add again and again. So this is kind of the for loop or the while loop which we use in our programming languages. So this jump command does that. It points again to the 0 address, so it will make the counter 0. It will makes the counter jump to the 0 address, so it will be start doing this again and again. So I will demonstrate the same here. We will switch back to the normal mode, reset everything, and I will give it a stable pulse, which is this automatic pulse, and this is supposed to count from 1 to 255. It is counting. Now I can increase the speed of this computer. You can see the effect when I change the speed of this. We are counting fast. Now we are counting more fast. So this is the counting of 1, and similarly we can do 2, 3, or whatever we want. Sorry, there is some issue with it. That's not the point right now, but yeah, we can say if we want to count the table of 3, so we can put the data as 3 on the 15th. Last time we have put it as 1, now it is 3. Now we can do the same thing with 3. I will make it slow. Three, 6, 9, it will do that phase. So it will keep going until 255, because the maximum value on the 8 bits we can have 2 to the power 8 minus 1, which comes to 255. So we can have maximum of 255. Also we can, in the negative numbers, from the 2's complement concept, we can have the minimum value is minus 128 and the maximum is 127, but we will not go into that. But right now it is counting the table of 3, like so. We can perform the number of quite a large number of possible codes in this computer to understand how our computer, the devices which we use in our daily life, the mobile phones, how those work. And similarly, we did with the add command, we can have this multiply thing. So the multiply command almost uses all of our 16 bytes, leaving 1 byte, so it uses 15 bytes. So for doing multiplication we have to program the RAM with these commands. These commands will execute one by one, and we will see the multiplication of x into y, which we will put on the 14th and 15th position. So this is the command, or this is the code for this computer for doing multiplication. The same we write this in the C as, like we say, take a variable a, we take a variable b, and we do is a into b. We just say a into b, but on the back half of that compiler does this. The compiler translate that into the assembly language, which looks similar to this, not exactly this, because this is for our computer only. For different compilers, whoever made them has their different notation and different step in which they can achieve the same thing. So like this is for the multiply thing, and this code is for the Fibonacci series code. Like when we program these steps into our RAM, basically we will see here as the that Fibonacci series, which will use 0, 1, like that. It will keep like 0 and the 1 that will be starting, but it will keep going. So that way, yeah, this is the same we write in the C, and we get the same result. And similarly we can translate the same into our own assembly language, then we put it here and we can get the result here. So yeah, this was all. You can find the details regarding this computer under the description. We have attached the document regarding all the details are given in that document, like on which part which chip we have used, and like all the data sheet diagrams, all the pin instruction, and why and how this computer has only how it is able to perform only 1500 operations per second, and like why this transistor here, why this transistor here, why this resistor here. Everything we have covered in this document, which you can find under the description. Thank you for watching. Have a nice day.